Oh, folks, we are on to the best category of problem and algorithm in the world, shortest path problems. We're going to look at some different algorithms to handle this single source, shortest path type of problem. The algorithms we look at will take as input an undirected graph, similar to what we've done before, with no negative weights at the moment, because these can cause some problems we'll see later if there are negative distances you could travel or negative time or things like that. And we need a source vertex. In other framings of the problem, we'll have a goal vertex as well. Those won't be the kind that we look at today. If you're interested in that kind of thing, taking a more general algorithms or AI class would give you some really great approaches to the single source, single destination. But the types of algorithms we'll look at will actually give you the set of paths from that source to every other vertex, each with minimum total weight. So this is similar to our spanning tree problems, where we're looking for minimum things, the shortest, the minimum length or distance or cost path. But it's a little different because we don't need to include a connection with every vertex in forming a tree. We need sets of paths that take us from one source to every other vertex. And we'll get those from the algorithms that we look at. There can be multiple shortest paths in our results here. So the goal of these sorts of things is to be able to do things like navigating a map, a walking path, a road, etc. And typically, again, the average person is going to want them between 2 points. But if you have a limited graph, like the kinds that we'll look at, you can have algorithms that give you answers for many or all of the points on that graph, all of the vertexes, all of the vertices on that graph. So examples in the real world, the shortest distance between two places or between one place and everywhere else you can get from there, the shortest time to travel something, taking flights between cities and wanting the lowest cost, if it costs this much to get from A to B and this much to get from B to C, and routing things through the internet, where we want to minimize the time that it takes to get from one device to another, but you have to hop between many routers or many subnetworks. We'll look at two algorithms for finding shortest paths. The first one will be Dijkstra's algorithm. It's a greedy algorithm, and it works on directed and undirected graphs. It requires the edge weights to be non-negative, like I mentioned before, and its output will be the lengths or the paths from the source to all other vertices. It's actually pretty similar to Prim's algorithm in its style, and we'll see how in a moment. We start with the source vertex, where Prim just picked an arbitrary vertex, because there we were looking for a spanning tree. We only needed everybody to be connected to the structure. Here, we need everybody to be connected to our source, our starting location. We then can set up a table with these columns. V, the starting vertex, so every vertex will have a row in the table, just like Prim's did. Whether that vertex is fully known, in other words, whether we have evaluated or fully explored that vertex, seen all of the connections it has, and the distance d sub v. But this is the distance from S, our source, our starting location, whereas Prim's allowed us a distance to any vertex. And P sub v, the parent that corresponds to that minimum distance, which will still be sort of a single step back. We won't list S as the parent for all of them because they won't all be directly connected to S. The parents are going to indicate to us what comes right before this one on a path backwards to S. It's a greedy algorithm, as mentioned before. It will add the vertex V with the least cost path, D sub V. It uses a priority queue that's keyed on that distance, D sub V, to find the next vertex to use. And it requires a decrease key operation to update other vertices. So as we find shorter paths, then we might have to decrease the keys of things that are already in the priority queue, which, as we know, is not always the best operation to do in a priority queue, changing values once it's built, but it can be reasonably fast with the right types of priority queues. If we have the input of this graph G here, and we're looking for paths from A, this graph is an undirected graph like we described in the beginning, though Dijkstras can handle directed graphs as well. So we build our table with a row for every vertex. We assume that their distance to A is infinity for everyone but A, because we know its distance to A. And we mark them all as not fully known yet. Then we'll start off exploring A, because it's the only one that we know to explore right now. We see that it has edges to D and B, and we record those as the distance for B and the distance for D, and what their parent vertex is, which is A in this case. They're directly connected to A. Then we pick the minimum of those, and we see that D was the minimum because it had an edge cost of 1. And we see that it's connected to H and J. So we update their values from infinity to be 6 and 7 because it is the cost of their distance to D plus, the cost of the distance to D from A plus the cost to get to that node, H in this example. So the distance to D was 1, plus the 5 to get to H gives us 6, and the distance to get to D was 1, plus the 6 to get to J gives us 7. So we're storing total path cost or path weight, but we're only storing the parent who it's most recently connected to. And then we also mark D as being fully known. We have evaluated it fully. And we don't need to update B's value because the cost to get to D was 1 plus 4 would be 5. That's more than the value that B already has with its direct connection to A. So we don't update it. Then we explore B because B has this cost of 4. It's the next minimum. And we see that there's a way to get to C. And so we update C, we mark B as known, and we're done with that. We don't need to change J because even though B connects to it, 14 is much higher than the 7 we already have for it. Now this will be a little different from Prim's algorithm because we're only exploring the relationships on these longer paths to A. So we explore H, but H offers us nothing new because it has a connection to J that would cost more, less, or the same actually. No, more, because it would be 1 plus 5 plus 2, give us 8. So it's not going to be a change to that. We only mark H known, and we're done. We then explore J because it's got the next lowest cost. Because these costs are cumulative, some of the other ones like C on here are sitting and waiting for example, J to get expanded, evaluated. We evaluate J, that gives us updated costs for I and G, because J's cost plus the distance to them is less than infinity, so we update those. Then we update for things connected to C. That gives us values for E and F. We evaluate F, which gives us no new values because its costs to anywhere are more expensive than the costs we've already seen. We evaluate for E, and again, no new values for for I and for G. And now we've evaluated every node in the graph. And you can see we have a value for each node. That is the cost of a path to follow to get to that node from A. For example, let's take F. It reports its cost as being 9, which is the cost of walking 4, 4, 1 equals 9 from A. And it reports that its parent is C, so I know I could step backwards here and say if I needed a path to it, well, I know the last item on the path is F, the next last item on the path is C, C's parent is B, so I would go through B to get there, and B's parent is A, so I know that the path is A, B, C, F here. So all of the V, P sub V pairs give us the edges in the paths to get to a particular node. If we compare with Prim's algorithm, the major difference is going to be, obviously right away, that the distance values will, many of them, be much larger than Prim's, because we're not looking at just direct connections, like the cost of 1 to get to F from C. We're looking at the cost to get to F from A, which is a much longer path, costs more. The structure also differs a little bit because we're not just picking, again, those shortest single connections to something. We're not just trying to make sure that everyone is connected to each other. We're trying to make sure that we know how everyone is connected to A specifically. So there are some areas in which the structures will differ because of the fact that we're looking for connections from A. We wouldn't want to have to get to H by coming all the way out and around through the graph to get there. But to include H in the spanning tree, of course it's cheapest to connect it from J so that we are connecting everyone to everyone else. We don't really care about specific distances from one particular node. So to outline Dijkstra's algorithm in pseudocode, we initialize that table that has the distances, has a row for each vertex, etc. We set everyone's distances to infinity except for S, our starting location, our starting vertex. They are all not known, and they all have no parent so far. While our priority queue is not empty, we get the minimum cost vertex off of that priority queue, and for every vertex that's a neighbor of that vertex U that we pulled off of the priority queue and is not already known, evaluated fully, then we look and we see if the distance to U plus the direct distance, the weight to get to that node, is less than the current recorded distance for that node, then we update the node. We update its parent to be U instead of whatever it was before, and we update its distance to be the distance to U plus the distance to get from U to this new vertex W. We then also have to decrease the key of W wherever it's currently living in the priority queue. And that's because we just found a shorter path to it. And so we want to make sure that W gets explored in the right order, because Dijkstra's algorithm relies on this ordering of picking up the next minimum and the next minimum and the next, but those minimums might change as we find shorter paths to get to something. We might have a very expensive edge from A to another node, say it costs 1,000, and we might find that a path that takes a few jumps around the graph with very low cost edges, like say they're each 1, and gets us to that other node cheaply, that's important to know. And Dijkstra's relies on the fact that we're selecting that minimum to know that at every time that d sub u for the node that we are fully knowing now is the lowest it can possibly be. We've already evaluated everything we need to know the minimum of this node u, and now we're just seeing if we can find shorter paths to its children, its neighbors, the nodes that it has edges to, like w. Delete min in Dijkstra's algorithm is called once for each vertex, and decrease key will be called on the order of the number of edges times. It may not be called that many times. Delete min will be called for all of the vertices. So it's the number of vertexes times the cost of deleting the min, plus possibly the number of edges times the cost of decreasing key. So these two will depend on the data structure you use. So for an array, delete min will be O of v, more expensive, but decrease key would be very cheap. For our standard binary heap, the delete min would be log v, so it would be v log v for that part, and the decrease key would also be log v, which would be e log v. We typically assume that there are more edges than there are vertices, or equal, less than or equal to, because Dijkstra's needs to be done on connected graphs so that we can actually know that there are paths, or discover that there are not, I suppose, on unconnected. But for a Fibonacci heap, which is a specialized type of heap, we can get delete min with log v, and we can get the decrease key in amortized time in O of 1. So we actually can get v log v performance in Dijkstra's algorithm if we use this specialized Fibonacci heap. One quick divergence here. Why wouldn't we allow negative weights? Well, it's hard to say what the shortest path is from A to C in this example here. Is the shortest path to go 3 and get straight there, or is the shortest path to go a longer distance of 6, but then somehow lose some distance you've traveled and knock it back down to 2? So these sorts of negative costs are unrealistic in a lot of the problems we would use Dijkstra's algorithm for. Can we somehow, by driving further, go back in time and get there before we left? Typically, I would say that's not going to happen to us. There may be problems in which these negative weights are necessary, and we'll look at some of those. But when there are negative weights for something like Dijkstra's algorithm, it confuses this concept of the minimum of the shortest path and makes it not possible to get those minimum values. Some people might say that we could just add a certain amount to every edge and make them all positive that way. But adding some constant amount to each edge would make the paths with more edges sort of weightier than they should be. It would linearly increase the distance of those longer edges and disrupt the structure of our graph there. We can't just, because these only have a single connection to each other, it might be okay, but in a larger, more connected graph, those longer paths would be hit harder by adding a constant to everything. So Dijkstra's algorithm can give us shortest paths from some starting node to every other vertex, every other node in the graph. And those paths that we get for those will be the minimum weight, minimum cost. It's got some limitations in terms of speed, with these having to decrease keys as we go. And it's got some limitations in terms of negative weights, but it can be a very powerful algorithm for solving these shortest path or lowest cost type of problems.